Hello, everyone. Thank you for joining me. My name is Christian DeLucia, and today I'm going to be talking about the ordinary least squares regression model. So the purpose of this video is to discuss the standard linear regression model, which from a technical perspective is typically referred to as the ordinary least squares model. I'm going to discuss some important concepts and show how to run the analysis, or at least a version of the analysis, using SPSS software. First off, let's think about what regression is. Regression is a very flexible modeling framework that allows for the prediction of a continuous outcome variable from one or more predictor variables. And by continuous there, I just mean that the outcome variable is a random variable that can take on lots of different values, as opposed to a categorical variable that has a finite number of response options. On the predictor side, however, predictor variables can take on any form. They can be categorical predictors, they can be continuous predictors, interactions between those predictor types, and so lots of flexibility on the predictor side, okay? As an example, a researcher might be interested in predicting frequency of substance use during adolescence from three predictive variables: age, gender, and peer attitudes towards substance use. Here I've got a conceptual model based on the example I just provided. On the left-hand side of the equal sign, we've got frequency of substance use. That's going to be the outcome variable. In this case, on the right-hand side of the equal sign, we've got three predictors: age, gender, and peer attitudes towards substance use. Okay. Some basic terminology. Predictors might be referred to as predictor variables. They might be referred to as regressors or independent variables, often abbreviated IVs. Okay. The outcome might be referred to as an outcome or criterion variable or a dependent variable, which is often abbreviated DV. And language tends to vary by discipline, and that can sometimes trip students up. So to illustrate some basic concepts, I'm going to walk through an example in which we predict self-esteem from two predictive variables: anxiety symptoms and trauma symptoms. And this model is based on some data that I collected from young adults, or mostly young adults, receiving short-term residential treatment for substance use disorders. So this example is based on some real data that my research group collected a couple of years ago. On this slide, I present the statistical model. I'm not gonna get too deep into the nuances of the statistical model, but I wanted to show the equation because this is the kind of equation that you'll often see in a statistics textbook. And for people who are out of practice of working with these kinds of models, this equation might look a little more formidable than it is. And so I just wanted to talk through it at a basic level, and then at some point we'll integrate the conceptual and the statistical models. Okay, we typically use Y to denote the outcome variable in a model like this. So on the left-hand side of the equal sign, we've got Y sub I. Now remember, in our example that we're going to work with, self-esteem is the outcome variable. And so on the left-hand side of the equal sign, we would have the various individuals on the data file. We would have their scores of on self-esteem reflected there. Okay. On the right-hand side of the equal sign, we've got A, which is meant to denote the y-intercept, and that's labeled the constant in SPSS output. Technically, the y-intercept is the predicted value of the outcome variable when all predictive variables have a value of numerical 0. Okay. And then our second term on the right-hand side of the equal sign is B1 X1. B1 is partial regression coefficient for our first predictor, which is general anxiety symptoms in this case, and it's denoted by X1. And then to the right of that term, we've got B2 X2. B2 is the partial regression coefficient for our second predictor, which happens to be trauma symptoms. in this case. And then on the far right, we've got E, which is our error in prediction or our residual, okay? Some of the terms carry an I or person level subscript. And for those elements, it just means that those those items can vary over individuals. So different individuals on the data file can have different levels of self-esteem. They can have different levels of anxiety symptoms, different levels of trauma symptoms, and then the model can fit individuals differently as well. And so they'll have the potential for different error terms or residual terms, okay? The last thing I want to say is that the um, the model is a linear model, and today we're going to be looking at linear associations only. And when we look at a picture of the results, I'll go into more detail in terms of what that means. So now I'm going to pop over to the SPSS environment, and I'm going to go ahead and run the model. Okay, so here's the data view of my data file. I've got 4 variables on the data file, the ID variable and the 3 variables of interest to our analysis. So to run the regression model, I'm going to start at Analyze. I'm going to select Regression. And then within regression, I'm going to select Linear Regression. I'm going to move S-esteem, which is self-esteem, over into the dependent box because that is our dependent variable or outcome variable. I'm going to move anxiety and trauma symptoms over to the independence box. Those are our predictor variables, which SPSS labels independence here. Then I'm going to click on the statistics tab. And in addition to what's checked by default, I'm going to check part and partial correlations, and you could check other things, descriptives, collinearity diagnostics. I'm not going to do any of that right now. I'm going to say continue. And at that point, that's all we need to get some basic output. So I'm going to click OK, and SPSS is going to generate the output for us. From a standard run like this, there are 3 basic tables in the output. The first one is the model summary table. The second one is the ANOVA summary table. And then the third table is the coefficients table. I'm going to go back to PowerPoint and talk through those output tables in a little bit more detail. I just want to mention I'm not going to talk through every element of every table. I'm going to hit the high points. So in the model summary table, I've drawn an arrow to the R-squared estimate. This is a multiple R-squared estimate in our case because we've got 2 predictors in the model. And we interpret R-squares as the proportion of outcome variance that can be explained by the model. So in our case, this R square of 0.116 or 11.6% of the variance is telling us that our 2 predictors, anxiety and trauma symptoms, are accounting for about 11.6% of the variability in self-esteem. Okay, next we have our ANOVA summary table. And for those of you familiar with the analysis variance, this table will look at least vaguely familiar to you. Okay, we've got sums of squares, degrees of freedom, mean square, our F ratio, significance, value. And so in the context of regression analysis, sums of squares regression can be thought of as the piece of the model that offers prediction. Sum of squares residual can be thought of as the piece of the model associated with lack of prediction or error or residual variability. Okay, and in the basic ANOVA framework, we take a sums of squares estimate divided by a relevant degrees of freedom estimate that gives us a mean square. Our F ratio is actually a ratio of mean square regression to mean square residual. Our F ratio is 12.1. 0.957 in this case. The p-value or significance level associated with it is less than 0.001. And so this is telling us that our overall analysis is statistically significant. Another way we could think about this is that the R-square estimate of 0.116 that we were looking at on the prior slide is significantly different than 0. Okay. So now I want to stay with the ANOVA summary table for a couple more slides and just show that we can take sums of squares total and we could divide it into two additive elements, sums of squares regression and sums of squares residual. Okay, sums of squares total can be thought of as the total variability associated with our outcome variable, which in this case is self-esteem. Okay. On the next slide, I'm going to take each term in that equation, I'm going to divide it by sums of squares total. Okay, so I'm going to, on the left-hand side of the equal sign, I'm going to divide sums of squares total by itself. And the first term on the right-hand side of the equal sign, I'm going to divide sums of squares regression by sums of squares total. And then the second term there to the right of the plus sign, I'm going to divide sums of squares residual by sums of squares total. And then at the bottom of this slide, we can see that we end up with this identity where 1 equals r squared plus 1 minus r squared. Now remember, we defined r squared as the proportion of variability in the outcome that can be attributed to the model. And so I just wanted to show this is how we sort of get that number numerically, right? And then rather than using to define the sums of squares residual or a lack of prediction in this case, I wrote it in terms of 1 minus r squared, which is an important quantity in statistics. Okay, so now let's move on to the coefficients table. The coefficients table has a lot going on. So let me just start by talking through the rows. And so our top row is labeled a constant. That's our y-intercept in the model. Okay, then we've got a row for each of our two predictor variables, in this case, anxiety and trauma symptoms. The first columns after our predictors are unstandardized regression coefficient and its standard error. Okay, and then our next column over gives us the standardized regression coefficients. These are often referred to as standardized betas. Okay. Now, and next we see we've got t statistics here. If we take our unstandardized regression coefficient divided by its standard error, that quantity is distributed as a t-statistic on n minus k minus 1 degrees of freedom, where k is the number of predictors in the model, and we can look up our t-value there to see what the probability associated with that value is. In this case, it's 0.127, which is above the industry standard of 0.05. So we would say that anxiety is a non-significant predictor here. In contrast, trauma is a significant predictor of self-esteem because the p-value there, significance level, is less than the industry standard of 0.05. Okay, so if we look at our trauma coefficient, we see that it is negative, and that's telling us that as individuals report higher levels of trauma symptoms, they're reporting lower levels of self-esteem. So as you move up on trauma or up on our predictor variable, you're moving down on predicted self-esteem levels. Okay. And then on the far right in this table, we've got 3 kinds of correlations that SPSS will print out for us. They label those correlations the zero order, the partial, and the part. A zero order correlation in this context is just the correlation between the predictor and the outcome without considering any other information, without considering information related to the other predictors in the model. okay? The partial correlation is the correlation between the predictor in question and the outcome, removing the effects of the other predictors from both the outcome variable and the predictor in question. Okay, so in statistics, we often say that when we're looking at partial correlations, that both the outcome and the predictor in question, both of those variables have been residualized for the presence of the other predictors in the model. Okay, and then the final correlation here, the one that SPSS labels the part correlation, is typically referred to in the statistics literature as the semi-partial correlation. And for that correlation, um, we get to see the association between the predictor and the outcome with the effects of the remaining predictors removed from the predictor in question. Okay, so for the semi-partial or the part correlation, the effects of the remaining predictors are removed from the predictor in question only, but not removed from the outcome variable, okay? At the lower portion of this slide, I created sort of a hybrid between our statistical model and our conceptual model. So I show that our outcome variable is self-esteem. For our A or Y intercept, I brought down the 2.455 from the coefficients table. And then for our first BX pairing, our first partial regression coefficient multiplied by our first predictor variable, I brought down our negative 0.018, which is the partial regression coefficient for anxiety. And then I just put multiplied by anxiety. And then for our second BX pairing, B2X2, I brought down our negative 0.01, which is the partial unstandardized regression coefficient for trauma. And I showed that we multiply that by trauma. And although the error term is not necessarily reflected in the coefficients table, I wanted to show that there's error in prediction, generally speaking, and it's always good to sort of be mindful of the idea that our models fail to predict. Oftentimes in the social sciences, fail to predict the vast majority of variability in the outcome variable. Okay. Now, one last thing I want to say here is that when we have two or more predictors in the model, the test of statistical significance of each of the individual predictors is an incremental variance test. And what I mean by that is if the predictor in question predicts incremental variance in the outcome over and above all of the other predictors in the model, then that predictor will be statistically significant. And so in the present example, that is true for trauma symptoms, but not true for general anxiety symptoms. So another way of thinking about that is that the trauma predictor here is accounting for significant incremental variance in self-esteem over the effects of anxiety, but anxiety is not accounting for significant incremental variance in self-esteem over the effects of trauma. Okay, so a lot of times when authors are writing the results of multiple regression models in manuscripts, they might use language like, in this case, we might say trauma was a significant negative predictor of self-esteem independent or over the effects of anxiety. Okay. All right, so next I want to show the partial regression plot. And there's a tab in the SPSS environment labeled plots. And on that tab, if you click on it, you could check a box that says create all partial regression plots. What this kind of plot does for us is it allows us to take the results from a multiple predictor model. If we were to graph the results from a two predictor model, the graph would really occur in a three-dimensional space. We'd have two dimensions associated with the predictors and a third dimension associated with the outcome variable. And as dimensionality increases, it's sort of hard for most people who don't work with those plots regularly to interpret them. And so we have a cheat here available to us in SPSS where we can, for each of the predictor variables, we can ask SPSS to generate a plot, and it generates these partial regression plots that are in a two-dimensional space, a little easier to interpret. And this plot is showing us the partial association between trauma symptoms and self-esteem, and the R-square associated with the line here is 0.05. And if we took the partial correlation from our output table and squared it, we'd get 0.05 within rounding, okay? And then in the basic linear model, like the one we're looking at, we could see that the line in the picture is a straight line without any bends in it. And that's just telling us that the rate of change in predicted y is constant over the full range of x values here. So for every 1 unit increase in x, predicted y goes down by a constant rate, okay? And that rate is whatever the unstandardized regression coefficient is. As the additive effects simultaneous entry model, okay, um, we could we could also test for interactions between or among various predictor variables. And so we could, extend the model. In the current case, we could have extended the model to include the interaction between anxiety symptoms and trauma symptoms. We can also structure models to test for indirect effects of the predictors on outcomes or mediated effects. We can also test for nonlinear associations between predictors and outcomes. For example, we might want to see if there's a quadratic association between study time and exam performance. And the idea being there that the association between study time and exam performance might be increasing and linear up to a certain point and then sort of flatten out, in which case that association might look more quadratic or at least have a non-trivial quadratic component. And we could model that in this framework by adding a predictor that would capture the quadratic trend. And I'll probably do a subsequent video that talks about how to structure and test those kinds of effects. And finally, um, in addition to being interested in whether or not the overall model is statistically significant or whether the individual predictors are statistically significant in their own right, researchers might be interested in sort of a middle ground approach where you can evaluate sets of predictive variables for statistical significance. And we could use an approach called hierarchical regression analysis to examine those kinds of questions. And then finally, I want to give a caution about causality that you often see discussed in the context of these kinds of regression models. Although the basic structure of the model makes a distinction between the outcome and the predictor variables, and that distinction sort of raises the specter of causality, we have to remember that causal inferences are based not only on statistical association, which our regression model can help us establish, but also other things as well, like temporal precedence between the predictors and the outcomes or the putative causes and their effects, and also ruling out possible spurious associations or, third variable influences. Okay, so causal inferences are, rely on statistics, but also rely on considerations that are beyond the statistics realm. And so I just wanted to leave you with a caution regarding causality. Here are some awesome references for the multiple regression model, and these are, great sources that you could pick up and learn a lot more about these kinds of models. I hope you enjoyed today's video, and I'm hoping to make additional videos that will cover additional ways to use multiple regression to answer interesting research questions. Thank you for watching.